Welcome to the 3.4 lesson video. Today we're going to be learning about linear programming. So I'm going to begin by telling you what that means. And our goal is to solve systems of inequality, specifically using linear programming. So let's talk about what this process is. Linear programming is a method for finding a minimum or maximum value of some quantity given a set of constraints. And another word for constraints is limitations. So you can see right here in this example that we have a system of linear inequalities, and because the domain and range are limited by these inequalities, these are called constraints. As you can see in the graph at right, the region that is formed by the linear inequality boundary lines and the shading, overlapping of the shading, that's called the feasible region. And the feasible region is the graph of the system, and it contains all the points that satisfy all of the constraints or all of the linear inequalities. An objective function is one more term that we're going to be discussing today before we get to examples. An objective function is an equation that models the quantity that we are minimizing or maximizing. So for example, two examples of minimizing something would be minimizing cost or minimizing time. And two examples for maximizing something would be maximizing profit or maximizing items produced. So you can see at right we have an example equation for an objective function, and that is 2x plus y equals c, where c is some positive number. And you can see right there that we have the feasible region in the yellow, surrounded by the boundary lines of the inequalities, and we have two red objective functions, and the only difference between them is the value of c. The graphs of the objective function for the various values of c would be parallel lines. And when the lines are closer to the origin, those represent the smaller values of c, and those further away from the origin represent bigger values of c. So you can see right here that the line 2x plus y equals 7 is intersecting the feasible region at the coordinate point 2, 3, and the other objective function 2x plus y equals 17 is intersecting the feasible region at the coordinate 7, 3. These vertices of the feasible region represent the least and the greatest values for the objective function. Basically, you need to realize that the domain is going to be restricted, typically for real-world situations. And we've actually been working with this already this year when we are talking about, for example, the number of people. That variable would not be negative. So that would be restricting the domain, which means we have some constraints that we're dealing with. And as in the previous lesson, the most reasonable method to determine the common solutions of a set of inequalities is to graph. So that's what we're about to do. In our key concept box here, we're going to be talking about the Vertex Principle of linear programming. This is something important and you want to jot this down in your notes. So if we are having a maximum or minimum value of the linear objective function, it's going to occur at one or more vertices of the feasible region. And we actually looked at that above when I was talking about this example right here, the maximum and minimum values would be at the vertices. I'm assuming you remember what vertices or the word vertex in singular form means. A vertex is when two lines come together to form a corner. So now let's dive into example 1 and learn how to solve a problem using linear programming by testing in the objective function all of the vertices of the feasible region. So here in example 1, we need to figure out what point in the feasible region maximizes the function p for the objective function p equals 2x plus y. So you can see at right that we're given the constraints. So take a moment to jot down these 4 constraints. These are all linear inequalities, and as usual, we're about to graph. And as in the past, we typically solve for y to put it in slope-intercept form to graph easily. So you can see what I did was I just solved for y, so I subtracted the x and I divided by 2. So I'm getting y is less than or equal to negative 1/2 x plus 5/2, and then I just put it in decimal form just to show you that 5/2 is the same thing as 2.5. So now what I'm going to do is graph that function. And I'm going to go to 2.5 on the y-axis. And then the slope is negative 1/2, so I'm just going to go down 1 and over 2. And then connect with a solid boundary line. I'm also going to be shading below because the inequality symbol is less than or equal to. As you can see, the skills that we practice in Chapter 2 are necessary for this problem. So now I'm going to do a similar thing and solve for y for the second inequality. When solving for y for the second inequality, I get y is greater than or equal to x minus 2. So I'm going to go to minus 2 on the y-axis, and the slope is 1 over 1, so that means we're going up 1 over 1. This is also going to be a solid boundary line because we have a line underneath the inequality symbol, and we're going to be shading above. For the third inequality, it is just x is greater than or equal to 0, which means it's a vertical line going through the origin, and all values that are greater than or equal to 0 are solutions. And for the last inequality, it is y is greater than or equal to 0, which means it's a horizontal line starting at the x-axis and going above. So now I'll show you the overlap. Okay, now that we have all of the linear inequalities graphed, you can see the overlap is that quadrilateral looking shape that is outlined in the thick black pen. And now we're given 4 different vertices. Those are all vertices of this feasible region. Now what we're going to do is use these vertices and evaluate the function p at each of these vertices to see which value we get for the biggest. That will be the maximum value. Okay, so I erased some of the highlighting and drawing on the graph so it's easier to focus on what we need to deal with. So the vertices are highlighted in the purple, and then you probably remember from geometry class last year that typically we label vertices with letters to identify them. So I wrote down the coordinates of the vertices, Q, R, S, T, and now we're going to be evaluating the function p equals 2x plus y, and evaluating just means plugging in the values for the equation. So we're going to be using the equation p equals 2 times 0 plus 0, and that equals 0. Let's try the next one. 2 times 0 plus 2.5, that equals 2.5. 2 times 3 plus 1, that equals 7. And 2 times 2 plus 0, that equals 4. So we wanted to figure out what point in the feasible region, which is this quadrilateral shape here, maximizes the function p. And we can see that the coordinate s, because we substitute that value, when we substitute that value in for the objective function, we find out that p equals 7, which means value for this function. Now we're about to take a look at a real-life example problem and discover the process of how to use linear programming to maximize profit. Here's example 2. You are screen printing t-shirts and sweatshirts to sell at the Polk County Blues Festival and are working with the following constraints. You have at most 20 hours to make shirts, you want to spend no more than $600 on supplies, and you want to have at least 50 items to sell. We need to figure out how many t-shirts and how many sweatshirts should you make to maximize your profit, and how much is the maximum profit. So let's take a moment and look at the givens and then identify the variables. I'm going to let x equal the number of t-shirts made and y equal the number of sweatshirts made. So let's use this table to organize the information that we have. Let's focus in on the first row for the minutes. It says here in the picture that it takes 10 minutes to make one colored t-shirt. So I'm going to write 10x. And for sweatshirts, it takes 30 minutes to make, so 30y. And our first constraint said we have at most 20 hours. Hopefully you're realizing that the units are different, minutes versus hours. So in order to make the total into minutes, we just need to multiply 20 times 60, and that gives us 1,200 minutes. So here is our first row complete, and the symbol that we want to use is going to be less than or equal to, because we do not want to go over the 20 hours, or also known as the 1,200 minutes. Now let's take a look at the number of t-shirts and sweatshirts. It says that we want to have at least 50 items to sell, so that tells me that we need to have 50 at the total. for the minimum actually. So that means we want a greater than or equal to, because 50 is the smallest amount of items that we want to sell. And then from there, we don't know the exact number, so that's why we have the variables x and y. The cost. It says here in the picture that supplies cost $4 for one t-shirt, so we're going to have 4x. And then for the sweatshirt, it says supplies cost $20, so 20y. And it told us that we do not want to spend more than $600. So we have 600 over here, and then we're going to have a less than or equal to, because we do not want to surpass that $600. So I wrote down the 3 constraints that we have so far in inequality form, and I just used the same values that we were talking about in the table. There are just 2 more constraints that we need to write down, and they should make sense to you. It's x is greater than or equal to 0, and y is greater than or equal to 0. And that's because since x and y are the number of t-shirts and sweatshirts respectively, we cannot have a negative number. So that's why we're starting at 0 and going beyond that. Now let's talk about how to come up with the objective function for the profit. So taking a look at the tags right here up in the picture, we see that the profit is $6 for a t-shirt and the profit for a sweatshirt is $20. So that's why I have 6x plus 20y. So that is going to be the objective function. And I know it's going to be for profit because it talks about in the question how many t-shirts, how many sweatshirts can we make to maximize the profit. So that's going to be our objective function. Okay, now that we made our objective function, if you are listening, if you could just put a smiley face right next to the equation that we just wrote down, that will help me determine who is actually listening through and watching the videos thoroughly. Now let's learn how to use this objective function. Before graphing the feasible region, I would just like to talk about how this function is a discrete function, and that's because the number of t-shirts x and the number of sweatshirts y can only be whole numbers. So remember, discrete just means we don't have all real numbers as solutions, only whole numbers work for this situation. So we're about to graph the constraints that we formed earlier to form the feasible region. So feel free to pause here to start setting up your graph. You can see that I used the variables that we defined earlier for the x and y labels. And you can also see that I'm going up on the x-axis, I'm going up by 15s, but I'm only labeling every other. And then on the y-axis, I'm going up by 3s, but again, I'm only labeling every other. When graphing the constraints, my suggestion is to either put the inequality in slope-intercept form or to find the x and y intercepts, plot those, and connect. I actually used the second process I just talked about. You can see right here, I pretended that it was an equation at first, and I found the x and y intercepts, plotted those, and connected those. And we're going to be shading below for this region because it's less than or equal to in the original inequality. For the next inequality, x plus y is greater than or equal to 50. I have this in the blue. I found out that the x and y intercepts are both at 50. I can easily graph this on the x-axis, but on the y-axis it's off the graph, so that's why I indicated it as an arrow. Now let's take a look at the third one. For the inequality 4x plus 20y is less than or equal to 600, I know that I'm shading below. And for the x-intercept, I found out that it's 150, and for the y-intercept, I found it's at 30. So I graphed this in the green, the x and y intercepts, and I connected them. The last 2 constraints are actually just the x and y axes, so that just tells us that we are working in the first quadrant only. So now I have the feasible region shaded. Remember, the feasible region is just where all of the individual linear inequality shading overlap. You may be wondering, how do we find the coordinates of each vertex? If they are hard to read off the graph, what we want to do is solve the system of equations related to the lines that intersect to form the vertex. So using that process that we have learned earlier in this chapter. So now I have labeled the feasible region with the vertices A, B, C, D. The vertex A is the coordinate 50, 0, and that is just the x-intercept of this equation here in the blue. And the D, the vertex D, the coordinate is 120, 0, and that is also the x-intercept of the other equation, as shown right here. For the coordinates of vertices B and C, we would need to solve these systems that I have listed right here. And in order to find out which systems I'm talking about, I just followed the color coordinating that I was using. So the blue and the green equations would be the intersection at vertex B. And then the red equation, which I show in the black up here, as well as the green equation, that would solve for the intersection point at vertex C. So just as in the previous problem, now I'm going to substitute each of these coordinates in for our objective function p equals 6x plus 20y to see which coordinate maximizes the equation. Okay, so I'm going to start off by plugging in 50, 0 for the equation. So 6 times 50 plus 20 times 0, and that gives us 300. Next coordinate, 6 times 25 plus 20 times 25, and that equals 650. For coordinate C, we have 6 times 75 plus 20 times 15, and that equals 750. And the last one, P equals 6 times 120 plus 20 times 0, and that equals 720. So like I said, I'm just using the coordinates of the vertices that I just discussed in step 2 and substitute those in for the objective function equation p equals 6x plus 20. And now we can see which coordinate maximizes the profit in this situation. So you can see that the greatest value is at coordinate C because we have p equals 750. So now let's discuss that. Like we were just talking about, at the coordinate C, 75, 15, the function is maximized. So that means we can maximize profit by selling 75 t-shirts and 15 sweatshirts, and I'm just getting that from the coordinate itself, x comma y. And the maximum profit at this coordinate is $750. So that completes our real life example. Okay, that's it for today's lesson. There were only 2 problems just because they were longer in length and difficulty. So now here's the lesson check. I am just looking for you to do the evens. So 2, 4, and 6. So take a moment to jot down these 3 systems of inequalities and constraints, and make sure you show your work and graphs for each of these. I'll see you soon.